So let us introduce a few more concepts. So the first concept is a contravariant vector. So suppose that we take an infinitesimal difference between two events, so dx mu. So dx mu is what we call a 4 vector. So let me use a different color. So dx mu is an example of a 4 vector. So it has 4 components, say dt, dx, dy, and dz. Now under Lorenz transformation, dx mu changes to dx prime of mu, and that's related to dx mu by mu nu dx nu. So a vector, the index on dx mu, which is upstairs, this is known as a contravariant index. And dx mu is an example of a contravariant vector. So any vector, such as say v of mu, it doesn't have to be the difference between two events that transforms under a Lorenz transformation in this way is called a contravariant vector. So this is what we call a contravariant vector. So next, we define what is a covariant vector. So what is a covariant vector? So, suppose that we have the derivative operator, say d by dx mu. So this is if you like, a 4 derivative vector. And we want to ask what happens when we do a Lorenz transformation. So we can write this as d by dx prime of nu divided by d of x mu d by dx prime of nu. Of course, because this nu index is repeated, it is summed over. Now, it's very easy to show that, what this is. So remember that from the previous section, we showed that dx prime of mu is lambda of mu nu dx nu. But of course, dx prime of mu is also the partial derivative of dx prime with respect to dx, say, rho times dx rho. In other words, we have mu nu is equal to, lambda mu nu is equal to dx prime of mu dx rho. Of course, the assumption here is that both x mu and x prime of mu, these are coordinates of inertial systems. So we can now use this in here, and we write that d of x of mu is equal to lambda of mu nu d by dx prime of nu. So now we can introduce a notation where we have delta downstairs mu as d by dx upstairs mu. And then we can say that under a Lorenz transformation, d of mu is transforms as, so this is related to this nu, lambda nu mu del prime of nu. But of course, we know what the inverse of this matrix is. The inverse of this matrix is simply, so if you have nu and mu, if we multiply this by, say, nu and rho, then, what is this? The first thing is the transpose matrix with nu and rho, and this is, say, nu and mu. So now we can write this as a matrix equation where we have lambda times lambda transpose, and we are looking at the rho mu element of it. But of course, we know that this is the inverse of this matrix, so this is going to be just rho mu. So we can use this. So what we can do is that we can multiply this thing with this equation on both sides and sum over the index, and then we can find that the transformed del downstairs mu, the derivative operator is given by del nu mu, del of nu. So this is an example of an object where this is a covariant index, and any vector, say w of mu, which transforms in this way, w prime of mu is lambda, say mu nu, w of nu, then this is called a covariant vector. Now, if I have a contravariant vector, then I can always create a covariant vector from this by taking, this should be a different index in nu, taking the metric tensor and summing over this common indices. So this summation process is called a contraction. So whenever we have two indices which are being summed over, that's called a contraction. So, what we know is that lambda transpose eta lambda is equal to eta. Now you can use this in this equation to show that if v of mu transforms as a contravariant vector, that is v prime mu is equal to lambda mu rho, v of rho, then v downstairs of nu transforms as a covariant vector. That is, it's going to be nu here, and that's going to be mu here, v of mu. So, of course, the repeated indices don't matter. What we call it mu, nu, alpha, beta, because we are summing over them. It is an example of what is known as a dummy index. So the first one is a contravariant vector. The second one is a covariant vector. So we can define a tensor to be something which has, say, it can have mixed indices. So this guy has two contravariant index and, say, one covariant index. And under Lorenz transformation, this will become T prime mu rho sigma, where the contravariant indices will each transform with a Lorenz transformation vector like so, and the covariant index will transform with the transpose of that. So this is sigma and gamma, so we have T alpha beta of gamma. So this is a general rank 2, 1 tensor. So anything that transforms like this is called a tensor. So next we want to discuss what do the Lorenz transformation explicitly look like. So the explicit forms. I mean, so far we have only said that Lorenz transformations are transformations whose matrices satisfy this equation. So that's a very abstract definition, but we can get more specific. And to get more specific, let's just derive some consequences of this equation. So if I take the determinant of this equation, what do we get? I get determinant of lambda transpose eta lambda is equal to the determinant of eta. We know that the determinant of the product of matrices is equal to the product of the determinant. So the left-hand side can be written as, say, delta of lambda transpose times determinant, sorry, not delta, determinant of lambda times determinant of eta, and on the right-hand side, we have determinant of eta. So these guys cancel out. Of course, the determinant of eta is plus 1. No, it's actually, what is it? 1, minus 1, minus 1, minus 1. So the determinant is going to be minus 1. So yeah. So then we also know that the determinant of a matrix does not change if we take the transpose of it. So this means that this is equal to the determinant of lambda squared is equal to plus 1. So that means the determinant of lambda has to be either plus 1 or minus 1. So there are two kinds of Lorentz transformation matrices. The first type is where the determinant of those matrices are plus 1, and the second kind are matrices whose determinants are minus 1. Now, there's a very famous identity, and the identity is that the log of the determinant of a matrix, say M, is equal to the trace of the log of that matrix. Now, of course, if we take the antilog of that, then we get determinant of M is equal to exponential of the trace of log of M. So using this, what we can say is that, well, let's define lambda to have the form e to the power I theta times t, where t is some matrix and theta is some parameter or a set of parameters, right? Then the determinant of lambda means that we are taking e to the power I theta trace of t. Now, if I say the determinant is plus 1, then the solution of that is that the trace of t has to be 0. So in other words, this matrix T has to be traceless. Now, so if I take such such a matrix that can be expressed in this form, then because we have a parameter theta, we can take that to be small, and then we can express this matrix as, say, 1 plus I theta times t. So what this means is that when theta is small, this matrix is infinitesimally close to the identity matrix. And in other words, the determinant of this thing is going to be 1 plus some order of, I don't know, theta or theta squared, something like this. So in other words, what I'm trying to say is that it's only the determinant equals to plus 1 Lorentz transformations are continuously connected to the identity. So if I take this expression and say, okay, I want to take, say, the determinant of lambda to be minus 1, and what does this mean for e to the power I theta trace of t? Now, trace of t is some number, let's call it tau, right? So we have e to the power I theta tau, and that is going to be equal to minus 1. So, we are in the realm of complex numbers. So what does this mean? This has only, what kind of solution does it have? So yeah, so the value of tau is fixed by definition. We are just going to assume that. Then what is the solution of this? The solution of this equation is that, theta of tau must be equal to pi, right? Because in complex numbers, this is what happens. This is where -1 is, and this is where +1 is. So in other words, theta has to be equal to pi by tau. Now, of course, we can see from this that tau, it cannot be that T cannot be a traceless matrix, because if it were a traceless matrix, then tau would be 0. So this thing, this is some particular number. This is some a finite number, because if it is going to be something infinitesimally small, then tau has to be infinitely large. So we are assuming that is not the case. So in other words, we see that this theta cannot be arbitrarily small. That's what I'm trying to argue. So what I'm trying to say is that the determinant equals to -1 is not something that we can express in this form, and therefore, we cannot take theta to be an arbitrarily small number, and therefore write it as being continuously connected to the identity. It's very easy to see that, the Lorenz transformation, which are of the form of, say, determinant -1, they have the form, say, well, this is called parity, is 1, -1, -1, -1. So this is a transformation which just reflects all the spatial coordinates through a mirror. And you can show very easily that there is no continuous transformation of your coordinate system that can continuously take you from xyz to -x, -y, -z. The other solution to this equation is where we reverse the time direction. This is called -1, 1, 1, 1. Again, you can show that there is no way to make a continuous transformation of our four-dimensional coordinate system such that only the time coordinate is reversed. So these are known as discrete transformations. So in this lecture, we won't discuss this anymore, but when we are discussing quantum field theory, we will come back to the discrete transformation. So in this lecture, we are interested in that part of the Lorentz transformation matrices which have +1 determinant. And it's easy to show that they form a closed set. So that if you make two consecutive Lorentz transformation, you remain in that set, which is not the true for the determinant equals to -1 Lorentz transformation. Because as you can see, if you make two, say, parity or time inversion transformation, you're going to get a determinant 1. So they do not form a closed set. Okay, so let's look at these transformations. So these transformations, there are actually 6 independent transformation. What do I mean by 6 independent transformations? There are 6 parameters, independent parameters. And 3 of them are rotations. And 3 are what we are going to call Lorentz boosts. So let's look at our interval, say dx squared. So this is ds squared. So this is minus dt squared plus dt squared minus, say, dx squared minus dy squared minus dz squared. Now, if I just make a rotation of the dx, dy, dz vector, by a rotation matrix, which you probably all know about, so R of, say, dx, dy, dz, then we know that, the length of this thing is going to be unchanged. The length of this thing is equal to the length of this. So in other words, if I make a rotation, ds is going to be equal to ds prime. ds squared is equal to ds prime squared. But here the dt part doesn't change. What changes are the spatial parts. So under rotation, these things don't change, and this, but this part is equal to this part. And for that to happen, the rotation matrices have to be orthogonal matrices. In other words, for example, if I do a rotation about the z-axis, then it'll have some form like cosine theta, sine of theta, minus sine of theta, cosine theta. There's 1, then there's 0, 0, 0, 0. And then the Lorentz transformation that is, part of that is reflects this transformation will have 1 here, and then 3 zeros here, 3 zeros here, and in this 3 by 3 block is going to be this rotation matrix. So these are the first type of Lorentz transformation. Of course, so this, let me call this, say, RZ, and then let's call theta. So this is going to be, this means that it's a rotation around the z-axis by the angle theta. So this is, one kind of Lorentz transformation. There will also be, lambda x, which will be a rotation around the x-axis, and then which will have the form of r of x here, and then there will be lambda y, which will be 1 of r of y. And I'm assuming that you're familiar with ry and rx and ry. So these are the first type of Lorentz transformation, which are rotations. And these Lorentz transformation form a closed set. So that is, if you just take a random string of these guys, and multiply them, that is also some rotation. Rotations form a closed set. In the language of group theory, we say that the rotations form a subgroup of the Lorentz group. So the second type of Lorentz transformation are called Lorentz boosts. And these are basically when the transformation that take you from one reference frame to another reference frame, which is moving with respect to the first reference frame with some velocity. So these are called the boosts. So how do we mathematically represent them? So to see how we can mathematically represent them, let's take some event whose coordinates are given by, say, t, x, and 0, 0, and we make a boost in the x direction so that the yz coordinates do not change. So we get x prime mu is t prime x prime 0, 0. And then, Lorentz, our special relativity tells us that the interval will be invariant. So we have t squared minus x squared is equal to t prime squared minus x prime squared. Now, this transformation is a one parameter transformation because, we have chosen the direction already, but what we need to choose now is the magnitude of the velocity. So we need to find a solution to this, to this relationship, which is a one parameter solution. Of course, this is very easy to do, and the solution to this is a linear, it has to be a linear transformation. T prime x prime must be related to t and x through a hyperbolic rotation. So this will be cosh of some parameter psi times sinh of the same parameter, and then sinh, and then cosh. So of course, this is some, let's call this matrix L, then the Lorentz transformation matrix is going to be L, and then there's going to be 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1. This will be our Lorentz transformation matrices. And this will be the boost along the x direction. Similarly, you can figure out what the Lorentz transformation matrices are, the boost along the y direction and the z direction. Maybe we should use a bit different notation from here. Yeah, so let's call this, say, lambda tilde. Right. Okay, so this parameter psi is called rapidity. And this is related to the physical velocity v by tan hyperbolic of psi. Now, it's easy to show using the relationship that cos squared psi minus sinh squared psi is 1, that this means that cos of psi is 1 over 1 minus v squared. And sinh of psi is v divided by 1 minus v squared square root. Of course, we are working in units where c equals to 1. If c was not equal to 1, then we would have a c squared here, 1 over c squared here, and we would have a c here. But we don't want to clutter up our notation by introducing a general unit. So if I do this, then of course the Lorentz transformation matrix that we just wrote down is going to have the form of 1 over 1 minus v squared square root v by 1 minus v squared 1 by v by 1 minus v squared square root 1 minus v squared. In other words, it takes the familiar form of Lorentz transformation that is usually taught in classes on special relativity. So, however, expressing our Lorentz transformation in terms of rapidity has an advantage over expressing it in terms of v. And that is, if I take two consecutive Lorentz transformation in the x direction with rapidity, say, psi1 and psi2, then the resulting transformation is a Lorentz transformation where the parameter is just the sum of the rapidities. Whereas on the other hand, if I write the same transformation but in terms of the corresponding velocities, say v1 and v2, then we get some velocity v3 here, and v3 is related to v1 like so. So v1 plus v2 divided by 1 plus v1 v2. So this is, of course, a lot more complicated formula, and this is the usual velocity addition formula that is also taught in classes on special relativity. And you can just derive this formula from here, just using the fact that this is the definition of v and relationship between v and rapidity. So I leave that as an exercise for you to do. And of course, if you take the velocities to be small, then of course this just gives you the result that you expected from Newtonian physics.